Hey everyone, welcome back. Grab those notebooks and get comfortable because today we are opening up the ultimate detective's case file. We're going to be reviewing everything we figured out in OpSciEd Unit 6.2. Specifically, we're looking at lessons 8 through 14. Now, I know you've got a big assessment coming up, and I want you to be absolutely 100% prepared to ace it. So think of this explainer as us getting together, laying out all our most crucial clues, and solving this massive scientific mystery once and for all. So here is our mental roadmap for today. First, we'll revisit the cup system mystery. Then we'll weigh light versus heat energy. After that, we zoom way in on particles and kinetic energy, figure out exactly what's happening when we're crossing the cup wall, lock down the direction of heat, and finally wrap it all up with acing your assessment. Consider this your ultimate study guide checklist. Okay, let's dive right into this with part 1, the cup system mystery, or as I like to call it, the case of the warming drink. Remember the big driving question that kicked this whole investigation off? It was simply this: how can containers keep stuff from warming up or cooling down? Now, on the surface, that sounds super simple, right? But as we quickly found out, the actual mechanics of how a cup does its job are incredibly complex and, honestly, pretty fascinating. Let's ground ourselves with what we figured out right at the start. Think about a cold, iced drink just sitting out there, warming up in the summer sun. We established pretty quickly that our cup is a closed system. It's got a lid on it. That means matter, the actual physical stuff, isn't entering or leaving the cup at all. But despite that, the water inside is still warming up, right? So if no warm matter is sneaking into our drink, then something else, some invisible process, has to be interacting with the cup system to cause that temperature change. Unless, ghosts are warming our drinks, we knew we had to go out and find some actual scientific suspects. And that brings us to part 2. Investigating our 2 main suspects that could be transferring energy into our cup: light and heat. Well, back in lesson 8, we tested out light. We shined lights on different cups in the classroom, we put some in the dark, and we discovered that light absolutely is a source of energy. Shining light warms water differently depending on the cup's surface, like whether it reflects, transmits, or absorbs that light. But actually, scratch that. It wasn't the whole story, was it? Because in lesson 9 with our water bath lab, we dug into thermal energy. And we found that when the temperature of a sample of matter in one system decreases, the temperature in the neighboring system increases. They directly affect each other. So we realized that heat, or even cold, can move right through the wall of the cup system, especially when there's a big temperature difference between the inside and the outside. To really understand how that magic happens, we had to put on our microscopic detective lenses. Let's move to part 3 and shift our focus to the particle level to see the unseen. Now listen up, because this is a massive concept for your assessment. We watched those simulations, remember the food coloring and the perfume spreading, and we figured out that matter is made of constantly moving particles. And this brings us to kinetic energy, which is just the energy of movement. You absolutely need to remember that hot liquids have particles that move faster, meaning they have way more kinetic energy. On the flip side, cold liquids have these sluggish, slow-moving particles, meaning they have much less kinetic energy. Now, what's really fascinating here is how we can actually model this invisible reality. When we draw out cold water, we use shorter arrows to show less movement and less kinetic energy. For hot water, we use longer arrows to show all that extra kinetic energy. But here is the real kicker. When these particles are buzzing around, they bump into each other. It's kind of like a microscopic game of bumper cars. When a faster-moving particle with lots of energy collides with a slower-moving one, it transfers some of that energy over. The faster one slows down a little bit, and the slower one speeds up. This collision and transfer of kinetic energy, that is exactly how an entire sample of water warms up. But wait a second. How does that energy from the outside air actually get through the solid plastic cup wall and into the water? Let's move to part 4, crossing the cup wall, to solve this part of the mystery. Think about how we modeled this setup. You've got the super spread out gas particles of the outside air on one side. On the exact opposite side, you've got the liquid water particles. And smack in the middle, tightly packed together, are the solid particles of the cup wall. That solid wall acts as a barrier, stopping the air particles from just freely mixing into the water. But remember, and this is key, even in a solid, particles are moving. They aren't flying around freely, sure, but they vibrate back and forth in place. It's kind of like people shivering shoulder to shoulder in a packed stadium. So here is the exact cause and effect storyline you're going to want to use to explain this scientifically on your test. Step 1. The fast, warmer outside air particles collide with the outside of the cup wall. Step 2. This collision transfers kinetic energy to the solid wall particles, causing them to vibrate more quickly in place and literally bump into their neighbors deeper inside the wall. Step 3. This chain reaction of collisions travels right through the solid wall until the inside wall particles finally collide with the slower, colder water particles inside the cup, transferring the energy directly to them. Boom, that is conduction in action. Okay, moving right along to part 5, the direction of heat. Because this brings up a massive debate we had in lesson 14. If a cold drink gets warm, is the cold leaking out or is the heat moving in? Do you guys remember the butter demonstration? We heated one end of a strip of aluminum foil with a candle, and we watched the butter melting way further down the strip. Why did that happen? Well, the candle provided energy to the particles in the foil right above it. Those particles moved faster, they gained kinetic energy, and then they collided with their slower neighbors, transferring energy all the way down the line until it reached the butter, causing it to melt. This gave us absolute, undeniable proof of directionality. Energy only transfers from an object that has more energy to one that has less energy. Cold isn't some magical substance that leaks out. Rather, heat is the energy moving into the cooler system. We have gathered the clues, we've analyzed the evidence, and we've built our models. It is time for part 6, bringing this case file to a close and prepping you for the final verdict. If you take away just one thing today, make it this universal rule. Burn this into your memory for the test. Energy is spontaneously transferred out of hotter regions or objects and into colder ones. Whenever you see a temperature change happening between two materials, it is always because higher energy particles are colliding with lower energy particles, transferring that energy down the line. That, my friends, is the definitive answer to our warming cup mystery. Which leaves us with one final, pretty provocative thought. Now that you know exactly how energy sneaks into a cup through light and through these microscopic particle collisions, how can you use these discoveries to design a cup feature that actually slows down this energy transfer? Think about reflective surfaces, double walls, maybe even air pockets. Keep those ideas bouncing around in your head as we head into our Lesson 15 Design Challenge. You've got all the evidence you need. Trust your models, trust your understanding of kinetic energy, and you're going to absolutely crush this assessment. Keep wondering, keep exploring, and I'll see you in class.